good day. So I'll discuss now the answer for the problem about crystallization, which is the coverage of the quiz 2 in unit operations 2. I'm Eric Hernandez. So the problem: a Swenson surface crystallizer is to be used to produce 10,000 kilograms per hour of crystals by cooling a saturated solution of magnesium sulfate that enters the crystallizer at 40 degrees Celsius. The slurry leaves at 20 degrees Celsius. Cooling water enters at 10 degrees Celsius and leaves at 30 degrees Celsius. The specific heat of the feed is 2.5 kJ per kilogram Kelvin. Calculate the cooling water requirement, kilogram per hour, and crystal recovery. So moving on to the problem. So the given are: C is 1000 kilogram, TF is equal to 40 degrees Celsius, TL, T1 is equal to 10 degrees Celsius, and T2 is equal to 30 degrees Celsius. And CPF is given also 2.5 kJ per kilogram Kelvin. So this is the diagram for the Swenson Walker crystallizer. So this is the entering cooling water, and it will go there. This is the T1, T2, then the feed will go right here, TF, CPF, and then this is called the magma, which composed of the liquor and the crystal, and TL, the temperature of the liquor is 20 degrees Celsius, and the crystals is given also, which is 1000 kilogram. So first, use the handbook and able to find for the kind of crystal. So I will show you how. So first, locate table 2-122 in the handbook. So there you will see the answer is MgSO4 7H2O. How did I find that? So first, I find for the temperature, which corresponds to the feed. So the given is MgSO4. So first, locate the MgSO4 in the solubility. It's here. So searching for it, it's right about here in this diagram. So I will locate 40 degrees Celsius and search if there is a corresponding solubility. So the only thing, the only MgSO4 with the corresponding 40 degrees Celsius temperature which has a solubility is the MgSO4 7H2O hydrate. So my answer is MgSO4 7H2O. So moving on to the solution, make an OMB balance. So F is equal to L plus C. Then the solute balance is equal to F. XF is equal to LXL plus CXC. So first, find XF, XL, and XC. So again, locate table 2-122, and there you will find that data with corresponding temperature. So the one that we use is the MgSO for the 7H2O. So it is written in the handbook, grams of anhydrous-soluble to 100 grams of water. So first, we will find XF at 40 degrees Celsius. So in the handbook, the data given is 45.6. So that is its solubility. So solving for it, XF is equal to 45.6 all over 45.6 plus 100, because this is a solution. So it is just like a mass fraction. So the answer is 0.31319. Next one is the XL for the liquor, which is XL at 20 degrees Celsius is equal to, in the handbook it's 35.5, so XL is equal to 35.5 divided by 35.5 plus 100, so this will be equal to 0.26199. Then next one is solving for XC. So XC is just the composition of the hydrate. So it is just anhydrous all over the hydrate. So MgSO4 all over the crystal form, which is MgSO4 7H2O. So just get the molecular weight. So 120.3 divided by 246.3, so the answer is 0.48843. So solving simultaneously, we now have the values of XF, XL, and XC. So just plugging in all the necessary data. So F is equal to L plus C. So C is given, so it's 1000. And then F times XF, which is 0.31319, is equal to L times XL, which is 0.26199 plus the crystals 1000 times 0.48843, which is the XC. And then solving it simultaneously, we'll have an answer of F is equal to 4,422.66 kg per hour, and the liquor's rate is 3,422.66 kilograms per hour. So how to find for the latent heat of crystallization? So locate table 2-182 heat of solution in the handbook. So convert units if necessary. So it's here at page 2-203. So this is the heat of solution in the handbook. So just browse this and find for the magnesium. So under the magnesium, and then so I get MgSO4 7H2 is equal to, so I get from the book the value is negative 3.18 kilocalorie per mole. So latent heat of crystallization is just the opposite of the heat of the latent heat of solution, so it will become positive, right? So LC is equal to positive 3.18 kilocalorie per mole. So I change this to joule per kilogram, so as to make the units homogeneous. So when you convert this, just multiply it by 1000 and then multiply it again to 4.4184 joule per kilogram Kelvin, and then divide it by its molecular weight. Divide it by the molecular weight of MgSO4, and then you will have this value, 54,019.98 joule per kilogram. So finding for the cooling water requirement, so first we have to set up for the heat balance. So heat balance is just equal to Q, and Q is equal to W times Cp, quantity T2 minus T1 is, and it's also equal to FCPF, TF minus TL plus CLC. So we have the value now for CLC. We have the value for TL, TF, CPF, is given. F, this part is for water, so T2 minus T1. Cp of water is, we all know that, so it's 4.187. Or if we change it, it will become 4,187. So, joule per kilogram Kelvin, and then W is the mass of the water, or the water rate. So just plugging in all the values. So W times Cp of the water times 303 minus 283, which is T2 and T1, is equal to F, which is 4,422.66 kg per hour, times CPF, which is given 2,500 joule per kilogram Kelvin. Don't forget to change the units, times 313 minus 293 plus 1,000, which is the crystal, 1,000, times LC. So we will have rate of water is equal to 3,285.80 kg per hour. So that is the water cooling requirement for this kind of crystallizer. And then finding for the crystal recovery, it's just solved by percentage of crystal recovery is equal to crystal form divided by the feed solution times 100. So we have the we have now the feed, the weight of the feed in the crystals form. So crystal recovery is equal to 1,000 kg divided by 4,422.66 kg times 100. So the answer there is 22.61%. So that's all. Thank you. Prepared by Eric Hernandez, Quiz 2, Crystallization. Swenson Crystallizer. Thank you.